All right. Oops. Okay. I think we got what we needed there. I think we're set. So, couple things. So I just kind of want to be aware we're a little, you do have some homework due today from the chapter 8 stuff. And then we've already been discussing chapter 9 and chapter 10. So why are we so far ahead on chapters 9 and chapters 10? They're two of the most important topics of the entire course. And you need to understand them a little bit. You can't really just learn hypothesis tests and then turn around and be able to be good enough at it to use on your project. It doesn't really work that way. You're going to have to kind of get these ideas, let them sink in a little bit, because hypothesis testing especially has some subtleties that students can really get confused about. And when you're new to thinking about hypothesis tests, some of the probability considerations can be a little bit tricky to think your way through. And I don't mean the p-value. When you calculate a p-value and then you make the decision to reject or fail to reject, like, that's all fine. But it's when you turn around and you start sort of making your conclusions, and what does it mean when we make these kind of conclusions, and what is the logic behind the hypothesis test, right? It's easy when you first walk up to it to think, oh, this is pretty simple, I get it. You get a p-value, you either reject or fail to reject, and then you make a decision from there. But you want to understand at a deeper level how that tool works. Otherwise, again, it's just crunching numbers. You're not actually doing anything, right? What is your purpose in the process if all you're doing is sort of reading something off of the StatCrunch? You have to be able to turn that into a problem, and you have to be able to understand the logic behind the test you're using in order to use the test correctly. Okay, so that's why we're talking about those. You absolutely should have multiple confidence intervals in your project. You should have multiple hypothesis tests in your project. And again, I don't just want to see you reading. Well, I don't just want to see you reading what StatCrunch told you. If StatCrunch gave you a confidence interval, great. Tell me what it is. But that's like minimal work. That's like very poor grade if that's all you do is, well, we ran a confidence interval for this proportion and we think it's here. Interpret it for me. Use the language that's used in the lessons and interpret that information so that I understand that you understand something, right? You're not going to go to a good grade in statistics because you can read a screen. You can push some buttons in StatCrunch and read a screen. You have to be able to interpret that stuff. So we're going to dive more into that today. Obviously, we do not have class on Thursday because it's Thanksgiving. And then we will meet up in a week. And then we'll, at that point, I think we largely will have talked about all the material. And then we'll be talking about, projects. You can bring questions about the projects. You can come to me with, your questions, your concerns. But just be aware, I do not really have a lot of freedom when it comes to extending things. So you have to be on target for making sure that you are going to finish the homework on time. You are going to finish your project on time. If that stuff doesn't get completed, you end up with an F, right? So make sure that you're going through. You might have to spend some time this weekend catching up on your homework. Some of you are great in terms of homework. Some of you are a little bit behind. So make sure. It may seem like, the semester is still a few weeks off. It's going to move very, very quickly. When we get back, it's going to be a few class meetings, and then boom, you're turning in your project, right? And I have to watch a lot of projects. It's a lot nicer to watch good projects than it is ones that were scrambling at the last minute and didn't really do the homework and don't really know what they're talking about. It's much more enjoyable to watch a well-constructed project. Plus, so that's kind of my own selfish goal, it's a little nicer to watch students when they've made really good work. But then also you as the student, you want a grade that's decent, right? You want to pass this class. You don't have to take it again. And some of you want an A. So maybe you're like, well, I'm not worried about passing, but I want my A. Well, that's all going to come from having those homework scores completed and, getting the homework done. Either way, whether it's passing or an A, whatever, it comes down to getting homework done and getting a decent grade on that project. Make sure that you kind of have things lined up about how you're going to record your video. I have students who use screen recording software. I have students who use their phone and then they print out graphs and then they do a voiceover. You have a lot of freedom in how you create this video. Do make sure that you turn it into me in a format that I can read. I have had a couple times, this has happened in the past with at least once, and I think maybe twice it happened with the final exam where someone sent me a file that I could not open, so then I can't read it. And then it's happened a couple times with homework where someone will send me a link to something, which is fine. I don't mind the link, but you send me a link to something that I don't have permission to open. So if you're going to send, like, your final project can't be a Google Doc, but, like, for instance, that's a thing that happens. Someone sends me a link to a Google Doc and they forget to give me, like, reading permission so that I can actually see the document, view the document. If that happens on the final exam, if your final project, I can't give, if I can't open an assignment, I have to give it a 0. So make sure that you're sending it to me in a format that is like a typical legitimate format. Best case scenario would be, put your video on your YouTube channel or your YouTube account or whatever, and then make sure that it's set to a setting where I can see it, and then send it to me. Right? You don't have to be embarrassed. It's not going to, your assignment is not going to go viral and then all of a sudden you're going to be on the front page of Reddit or something like that. You don't have to worry about that. But that's one way to do it. Post it on YouTube. Some people send me the actual file. Just make sure you're sending in a typical file that VLC can read or something like that. That is kind of a normal format to look at videos. Okay. And then, make use of the office hours between now and the end of the semester to come in and ask me those questions so that I can help you out. Almost always, I would say, when someone comes to me with a question about the project, even if they mostly know what's going on, I would say almost always I'm able to give them some feedback that helps them along. But that generally only works when the student comes in and says, okay, here's what I've done so far, and I'm not sure if I'm doing it right, or I'm not sure if this is what you want. You kind of have to come to me with some work already done so that I can look at your work and say, oh, okay, you're on the right track, but you should probably make this change, and you should consider making this other change. And if you do those things, I think it's going to be a better presentation of your statistics and a better way to communicate it. And then they go, oh, okay, that sounds good. I think I'll take those suggestions to heart, and I'll probably implement them in my project, and then it goes well. What you can't do is just show up and say, I don't understand hypothesis testing. Because if you literally understand 0 about hypothesis testing, then what is the starting point? Like, what feedback am I supposed to give? We're spending multiple classes talking about hypothesis testing, and you have the lessons and assessments. How could you show up with no understanding of hypothesis tests? So, put together what you think you can come up with, and then come see me and say, well, this is what I have, but I feel like I'm probably doing it wrong. What are we doing here? So, and then I can help you with that. But I kind of can't do much with an empty slate. If you literally don't understand anything about hypothesis testing, go back and watch the class meetings about hypothesis test. Go back and look at the lessons about hypothesis test. And make use of things. Excuse me. My voice is going out. Oh, I haven't had any water yet. What was I saying? And so that you can get your hypothesis testing stuff done, right? And I'm saying hypothesis test, but this kind of goes for any category, right? Any category, especially the ones where we had an assignment at the end that was the project-based one. So like at the end of chapter 9, there's a project here about estimating that parameter. That's a pretty good indication that you really want to include some stuff about that in your project. Right? So for instance, chapter 7 and 8, notice how at the end of 7 and 8, there isn't really a project assignment, a project discussion for you to work on. That's because a lot of your projects are not, it's going to be pretty hard to implement this for some of your projects. Some of you can, like this binomial stuff, you might be able to make a statement. But since there's no like project part there, I'm probably not going to like mark you down if you don't have a part of your project that's about distribution of the sample mean, because you only have one sample, so that would be kind of hard to discuss a little bit. So like with chapters 7 and 8, that stuff was really setting us up to understand chapters 8 and 9, or 9 and 10, I mean. Right, was really the kind of point of those chapters. But then 9 and 10, you want to include some stuff. These other chapters where we had conclusions, you probably should be updating those conclusions. If you're using the conclusions that you wrote down a month ago, they're probably not very good because you were just learning how to make those conclusions. Once you have the confidence intervals and the hypothesis tests under your belt, you're going to be able to make much more, I don't know if intellectual is the right word, but much more scholarly conclusions than you were a month ago, just because you've had more time to sit with the information and you understand statistics at a better level than you did a month ago, right? It's just natural. If you've been doing what you're supposed to be doing, which is learning statistics in the last month, you will be able to make better conclusions now. So make sure you do that. I mean, in a lot of ways, that's what separates a low-grade paper from a high-grade paper a lot of times, is those conclusions. The conclusions you make about your confidence intervals, the conclusions you make about your hypothesis test, the conclusions you make from your visuals, all that kind of stuff. That raises like a bottom-level paper, sometimes up to, it raises maybe up to a B, sometimes up to an A, depending on how well you handle those conclusions. So don't skimp on that. That's one that definitely, if you do that well, that can definitely draw my attention and go, this person seems like they understand how to use statistics because they're making really good conclusions from their data. Correlation, like why not, right? I watch some projects where people don't have any discussion of correlation. Why would you not? Like first of all, it's a big topic in the course, correlation and regression and all that kind of stuff. Plus, it's got a great visual that you can use. You put a scatter plot with your regression line on there. You give me an R value, and you talk about whether that, you interpret that R value for me, and then you show me the picture and tell me visually if you think it's a good regression line or not. Like that discussion that I just described will tell me, oh, this person was paying attention. This person figured out how to use correlation and regression, and it takes up, you could easily take up 4 minutes just talking about this, right? Doing it well. Again, don't try to hit a certain time, because that's almost like worse. Someone makes a 15-minute video that like clearly should have been 8, but they were trying to stretch it. That's almost worse to watch. So don't stretch just for the sake of time. But what I'm saying is, you should easily be able to talk for 4 minutes about your regression, correlation, your R value. Show me your scatter plot with the regression line in there. Sometimes people they give me a scatter plot with no regression line, and I think why not? Even if your argument is that the regression line is not a good one, that it's a poor model, show it to me and then talk about why it's a poor model. Give me the R value and say, look, we can even see that it's not a good representation, right? So, and also, again, don't be afraid of mistakes. I find a lot of times in these projects, students are trying to hide their mistakes like they somehow did a perfect project. You all just learned statistics. In fact, you haven't even finished learning it yet. So I'm not expecting you to have never made a mistake this whole semester. You should be making mistakes all over the place, right? That's part of learning. If you're not making mistakes in the learning process, then you're not really pushing yourself, right? You're not really trying that hard. So mistakes are fine. Talk about them, right? I've had the number one mistake that comes up is when people talk about their questions and go, yeah, I know we talked about it in class, but until I actually wrote questions and saw the feedback, I just didn't get how to write a good question. And so my questions, I had to throw them out. The data was so bad. Here's what I would do differently next time, right? What you just proved to me is that you learned something, right? If you give that discussion, we sort of have this society where we're all so afraid that people are going to judge us, and we're all so afraid of making mistakes. And if I make a mistake, it means I'm terrible at something, and I should just give up on this certain thing because I made a mistake at it once, and people are going to laugh at me, and then I'm going to feel bad and ashamed and embarrassed. And it's just nonsense. It's total nonsense. If the education process, you need to be making mistakes. That's how you learn. So don't hide from your mistakes. If you tell me about a mistake and explain how now you know how to do it right, then you've just proven that you learned something. That's what I'm looking for in these projects, is proof that you have learned statistics, so that I can go, yep, passing grade. You don't need to take statistics anymore. Congratulations. And you move forward. Right? So don't be afraid to tell me how your questions were bad and you would do it differently next time. This is what I learned from the questions that we asked. We messed it up, and here's the reason we messed it up. Next time I would do this. Great. You've learned how to do it better. So don't be afraid of that kind of stuff. Make sure your visuals are properly labeled. I mean, that's one of the most, it's like someone's putting a spotlight on your bad work. When you show a visual and you don't have your labels in there, you don't have a title, you don't have the units, then it really makes me wonder, because that would have taken seconds to put all that information in there, and you didn't do it. That's some really low effort work that I'm looking at, right? Really low effort work if you couldn't even label your visuals properly. So make sure, though, like, it puts me in that frame of mind then of thinking, this student, I think, maybe is putting very low effort into this. And that doesn't mean that your whole project is out, but that's the frame of mind you put me in. When you show me a visual that is like not labeled, doesn't have a title, I think, okay, I'm looking at a low effort project here, right? And you might get it back. You might prove with the rest of your project that no, actually they did put a lot of effort into this stuff, but I'm still going to be scratching my head going, why did they put such little effort into project visuals when that's actually a really easy thing to do, considering that StatCrunch does it all? Okay, so make sure those are properly labeled. I'll talk about more of this in the future again, but just kind of bringing it up because we're getting to the end. So I want to make sure that, especially, some people are going to work on the project this weekend. They're going to start putting that stuff out there. So I want to give you a little bit of a heads up and for now, so that you can start working on those things. Okay, with that said, let's get into some hypothesis testing values. So remember, the basics of a hypothesis test is that we have some things that we know are true, right? Facts, like legitimate facts, right? So they're not in question. And then we have one assumption. That is our hypothesis, the thing that we are trying to test. And what happens in a hypothesis test is we get a thing called a p-value. And that p-value, it's called p-value because it's a probability. It is the value of the probability. So it is the value of the probability of getting a measurement at least as unusual as the one that we are interested in, or more unusual. So you can loosely think of it as, what is the probability that this occurrence happened under these conditions? So you have a bunch of facts and one assumption. If the probability is so low as to be unbelievable, then what's the only thing that can be faulty? The only thing that can be wrong is your original hypothesis. So then what you would do is you reject the original hypothesis. If the probability of something is super, super low, we tend not to believe it, right? We go, I don't know. This seems sketchy. I think this is weird. It's the same situation in a hypothesis test. If your probability comes out 0.00001, like that means if we did this 1,000 times, this would occur once. That's pretty unlikely that that's what happened the one time we measured it. So you throw out that hypothesis test. What we say when we do that is that we reject the null. That's a phrase that you hear all the time when you talk about hypothesis tests. Oh, I rejected the null. I decided to reject the null. The other interpretation is that we fail to reject the null. Hold on one second. I got to get some water. Sorry about that. I keep my throat keeps getting dry. So those are there's basically, with the hypothesis test, there are two levels of conclusions that you want to make. One is interpreting the results of your hypothesis test directly in statistical terms. So when your p-value comes back, you're going to make a conclusion that we are going to reject the null hypothesis, or we are going to fail to reject the null hypothesis, right? So that's like the statistical conclusion in statistics terms. Do not stop there. If you just make that first conclusion and stop, that's in that realm of all you're really doing is pushing some buttons in StatCrunch and then reading a line that you may or may not even know what it means. So you have to give that conclusion, but you want to give another level of interpretation of the problem, another layer of conclusion, which is to state in the terms of the original problem your interpretation. We failed to reject the null. What does that mean in terms of our problem? So put it in the language of your original problem of, does this mean that we think that at least 50% of students work more than 30 hours a week? And like what is your conclusion in that original wording? You have to give that as well. Think of it this way. When you have say you go off and you have a job and you have to do some statistics at your job, which theoretically you'll want to have at least a basic understanding of statistics, because most of you are in this class because your major said at some point you have to take a statistics class, and so you are. So the assumption would be that they expect you to use statistics a little bit. So think about being at your job and you had to interpret some statistics. What does your boss want to hear? When you come in and you make your recommendation, they've said, can you go figure this out for us? Look at the statistics and then make a recommendation to us. Your boss doesn't want you to come in the room and say, hey, I got it all taken care of, boss. We're going to reject the null. Your boss is going to go, what are you talking about? I gave you some information about quality control, and if our machinery is okay, or if we need to upgrade the machinery, and you're coming back and you're talking to me about rejecting the null, I don't know what you're talking about, right? The conclusion that your boss wants to hear is either, yes, we need to buy new machinery so we can improve quality control, or no, we do not need to buy new machinery because quality control is okay. Do you see the difference there? When you have it in the terms of reject the null or fail to reject the null, no one's going to know what you're talking about. Because first of all, no one's read your hypothesis test. No one wants to read your hypothesis test. They just want the decision. Do we buy new machinery for next month, or do we not need to? Right? So you have to make that like the real world summary for your particular problem has to be in there. Okay? If you just say, well, we got this, I got a p-value, I rejected the null, then, not a good score for that. So make sure to include that, like I've talked about. And that's what they say here. If p is low, the null must go. That's just a fancy way of saying if your p-value is low enough, you reject the null hypothesis. If p is high, the null will fly. I think this is kind of silly myself, but whatever works for you to remember about the p-values. I think you don't really need nursery rhymes in order to remember it, but if you do, that's okay. Don't feel bad about that. A lot of things referred to as p in statistics. There's the p-value, which is a probability. So the p-value is the probability of getting a test statistic at least as extreme as the one representing sample data. So that's what your p-value is. When you run a hypothesis test and you get a p-value there, that's the probability of getting your results or more extreme. So if that value is very low, that means it's very unlikely to get the kind of situation that you're seeing, meaning we should reject the null hypothesis. This p is the population proportion, so don't mix those up, right? So I want to talk about, let's see, did I miss a page somewhere? Okay, I want to come back to this situation because I think it's a good explanation there are two types of, where was it? Okay, way down there. We'll come back to this in a second. It threw me off because the side thing, the example I'm going to give was up there. We'll save that for a minute. I forgot the order some of this stuff was in on this page. Okay, so we don't need that. Here we go. Decisions and conclusions, right? So the standard procedure for hypothesis testing requires that we directly test the null hypothesis, so our initial conclusion will always be one of the following. It is important to use this wording for the sort of surface level conclusion. If you mess this up, it really shows, oh, this person, they have zero understanding of a hypothesis test. So when you run your hypothesis test, your surface level conclusion, your shallow conclusion will either be that you reject the null hypothesis or you fail to reject the null hypothesis. Those are the wordings you should use, okay? When people start saying, oh, well, fail to reject the null hypothesis is the same as accepting the null hypothesis. No, it is not. It is a big difference. And it may seem like, there's my teacher just being strict about words again. It has to do with, I keep talking about this probability, the subtlety of the probability that lies behind this problem. We never really give evidence for the null hypothesis. We can show that it is very unlikely and we can reject it, but just because there's a high probability that that thing could occur doesn't mean it did occur, right? So, so for instance, if I start class late one day, and then I come on and I tell you, oh, sorry, everybody, I had to start class late because the power was off at my house. That's reasonably... There's a high probability that that's true. It doesn't mean it is true, though. It could have been some other reason. It could be that I slept late, or it could be that I, whatever, my computer wasn't plugged in, or there's lots of reasons it could be. So having a high probability doesn't support my claim that the power was off at my house, but the fact that there is a high probability that my story is plausible means that you're probably not going to challenge me on it. Right? You're probably not going to say, I don't buy your story. Like, I'm going to reject that. I'm going to reject what you're saying. It doesn't mean that you believe me. It's just that you don't really have evidence to reject the statement that I'm making. Okay? So that's what we're doing here. The null hypothesis never really gives evidence to the null. So that's why if you are trying to prove something, don't make it the null hypothesis. If you are trying to give evidence to a statement, make that the alternative hypothesis. That's how this works. If you want to make the statement that we think that the proportion of students who work more than 30 hours a week is above 60%. Okay, that could be the claim that you want to make. Then don't make that thing be the null hypothesis. If you want to give evidence to it, that needs to be your alternative hypothesis, and then your null hypothesis will just be the opposite, that the proportion is less than or equal to 60%, or whatever it was I said a minute ago. And then your goal in the problem would be to reject the null. If we reject the null, that means we are left with your alternative. Okay, but I know I will watch projects where people do this, where they set up a hypothesis test where their null hypothesis is the thing they want to show. They get a p-value of like 0.4, and they say, therefore, we've proven my statement. And that's not that logic fails with a hypothesis test because of the way the probabilities work in the problem. And I get that you probably are not all comfortable with that. But once you've sat with hypothesis testing for a while and that probability starts to make sense, you go, oh, I get why I couldn't make this statement that I wanted to make when I was in Intro to Stats. Okay? So just kind of remember that's the key. Whatever you are going to try to give evidence to in a hypothesis test, you make that the alternative hypothesis, and you make the complement, whatever the opposite of your statement is, you make that the null hypothesis, and you hope that that gets rejected. Okay? So on the surface level, we only ever use these terms, that I reject the null hypothesis or I fail to reject the null hypothesis. But again, that's just on the statistical, that's like your scratch work. You're not going to go in and tell your boss, hey, good news, we failed to reject the null hypothesis. He or she is going to say, what are you talking about? What does that mean? And then you're going to go, oh, what that means is we don't have to buy new equipment this month. Oh, okay, thanks. So see how there was the surface level, the shallow conclusion that is really just part of the test. And then there is the conclusion that is the humans can understand. That's where you are useful, is making that conclusion that humans can understand. If you're only doing the first part, then they're going to say, well, I could have anybody run a hypothesis test and tell me if we reject the null or not. I need someone who can like make a recommendation. Okay. We're just using the p-value method. That's how StatCrunch works. What's interesting is we can also use confidence intervals sometimes for this. So let's just say that you wanted to test the claim that 50% of students work more than 30 hours a week, right? Well, as a confidence interval, if you construct your confidence interval for the proportion and 0.5 lies in your confidence interval, well, then that means it's plausible. That means that there's a good chance that it's in there. So there are ways where you can do the same type of work with a confidence interval that you can with the hypothesis test. And that's why some journals, they'll tell you to use one or the other. They'll say, if you're going to submit research to our journal, you got to use confidence intervals, no hypothesis tests. Or sometimes a journal might have the other way around. Or if you're working at a company, maybe you go work at Amgen, they're going to say, oh, the way we do it here is when we turn in our lab reports, the statistics are done with confidence intervals. Or we do it with a hypothesis test of 0.01 alpha level or whatever. So that kind of changes. Sometimes you can choose what you think is best for your problem. Sometimes you're going to be working at a place where they say, this is how we do it here. And that's helpful too, because at least there's a consistency. So everyone kind of knows how they want the work done. Right. Okay. Wording the final conclusion. So that's kind of what I'm talking about. There's really two conclusions. They're talking about the final conclusion. Okay. So there's a little procedure here for summarizing, a procedure for wording the final conclusion in simple, non-technical terms. So your technical terms are things like never say accept, reject the null hypothesis, or fail to reject the null hypothesis. But again, that's not your final conclusion. That's like your preliminary conclusion. Note that only one case leads to wording indicating that the sample data actually support the conclusion. That's where students go wrong sometimes, is by thinking that they think they found support for their claim when they haven't, because they put it in the wrong hypothesis. Okay. If you want to support some claim, state it in a way such that it becomes the alternative hypothesis, and then hope that the null hypothesis gets rejected. So that's that statement. I keep saying that basically, and I repeat it because it seems like the more I repeat it, the fewer students do that in their project, which is good, because that's a pretty big infraction that you do. So just keep that in mind. If you want to support some claim, state it in such a way that it becomes the alternative hypothesis, and then hope that the null hypothesis gets rejected. What you cannot do is make the thing you want to support the null and then try to find evidence for the null. That's not how this test works. Okay? So never conclude a hypothesis test with the statement, reject the null hypothesis, or fail to reject the null hypothesis. Always make sense of the conclusion with a statement that uses simple, non-technical wording that addresses the original claim. Now, in this book, they're telling you not to use those phrases. I'm saying go ahead and use both, because I find that students feel a little more comfortable if they can say either reject the null or fail to reject the null hypothesis. But I do have the same expectation that they have in this book, which is make sense of your conclusion in the non-technical sense, in the original vocabulary of the problem, in terms of units students are taking, or hours worked by students or age or whatever it is that you're working on, make sure you put that conclusion back into the original language and say something interesting, right? No one's ever going to get excited because you tell them that you failed to reject the null, but they might get excited if you have some interesting statistical results, okay? Yeah, and I'm going to read a couple sentences here just because they're sort of, it's just another way of saying the thing that I've been trying to say. And so, you know, sometimes if you hear it in a slightly different way, a few more students are going to go, oh, I see what he's saying here. So you see here, a few textbooks continue to say accept the null hypothesis instead of fail to reject the null hypothesis. Very few books. I don't know of any that still do that. The term accept is somewhat misleading because it seems to imply incorrectly that the null hypothesis has been proved, but we can never prove a null hypothesis, right? That's if once you understand how the statistics behind the hypothesis test works, which takes a little time, so you may not be there yet, you realize, oh, I see why it can't support the null. We can only support the alternative, okay? The phrase fail to reject says more correctly that the available evidence isn't strong enough to warrant rejection of the null hypothesis, but it doesn't mean it's true. It just means you don't have enough evidence to you know, call someone out and say, I think you're lying here, or I think you're wrong. You don't have enough evidence to do that. But it doesn't mean that that thing is true, just that you miss the evidence to call them out. In this text, we use the terminology fail to reject the null hypothesis. Do not, in your projects, tell me that you're accepting the null hypothesis. That will automatically lose some points. You're going to get marked down if you say that you accept the null hypothesis, or you tell me that your hypothesis test gives you support for the null hypothesis, or that it proves your null hypothesis. That's going to be a big markdown on the hypothesis test section of the project. So make sure that it's subtle. I get that it's subtle. So make sure you're thinking about that when you're watching the videos and you're looking at the examples. Okay. Right. Okay, multiple negatives are confusing. They're definitely confusing, multiple negatives. Right, so when stating the final conclusion in non-technical terms, it is possible to get correct statements with up to 3 negative terms. So, for example, there is not sufficient evidence to warrant rejection of the claim of no difference between 0.5 and the population proportion. So that gets a little confusing when we keep throwing negatives out there. So there is not sufficient evidence to warrant rejection of the claim of no difference. Right? There's like three negatives in there, and it's not always immediately obvious what that means, first of all. So people listening to that have to sort of figure out what it means, but then you as the person doing the work can also get confused. So it's nice if you can rewrite that conclusion so that it's a little cleaner to understand. It's a little easier to understand. So try to do that if you can, but be careful. Okay, errors. When we have something that produces errors, most things that we deal with are not perfect, right? Even computers and calculators actually make mistakes from time to time and have errors in them, right? You see this if you're familiar with floating point operations in computers. They sometimes lead to errors. Basically everything at some point or another makes errors. A lot of times people assume that those errors are balanced or symmetric, and that's not always necessarily true. You have to think about, well, what are the type of errors that can be that can occur in this situation? And sometimes there's just the assumption that, like, okay, well, yeah, they must make the same errors in both directions, but that's not the case. So we have type 1 errors and type 2 errors. Type 1 error, the mistake of rejecting the null hypothesis when it is actually true. Okay, so the mistake of rejecting the null hypothesis when it is actually true. You won't know that you've done this, right? Because if we knew if we knew for sure what the actual value is, we wouldn't have run a hypothesis test in the first place. So every time you reject a null hypothesis, there's a tiny, tiny little chance that you shouldn't have. But you won't ever know, right? It's like if we were magic and we could sort of magically know these values, we wouldn't have to run these tests in the first place. So that's one type of error. So when we say error, I don't mean that you made a mistake. I just mean that in this case, statistics went the wrong direction. It made the wrong choice, right? When you deal with probabilities, you can be right most of the time, but occasionally things are going to come out wrong. So that is one type of error that can occur. We reject the null hypothesis because our p-value is really, really low. But in reality, in real life, if we could magically know the true value, we shouldn't have rejected the null hypothesis. That's one type of error. The other type of error, type 2 error, is the mistake of failing to reject the null hypothesis when it is actually false. So maybe we get a really high p-value, like 0.2. So we go, well, that's not low enough. I can't reject the null. And so we did the right thing for the test. It's just that in reality, this unknown value, actually we came to the wrong conclusion. Okay, so when I say error, it doesn't mean you did anything wrong. It doesn't mean the test did anything wrong. But, if you think about it, if you use probability with a 95% confidence, that means we expect to be right 95% of the time and wrong 5% of the time. So occasionally you're going to be wrong. You're going to make the wrong conclusion. And there's a little chart here about basically you've got that the null hypothesis is true in this column, the null hypothesis is false. We decide to reject the null hypothesis or we fail to reject the null hypothesis. So there's 4 outcomes. And 2 of the times we've made the correct decision, 2 of the times we won't. And you might go, oh, does that mean the test fails 50% of the time? No, because these happen, if we do it right, the orange ones happen very rarely, right? That happens more rarely. So let me give you an example up here of what I mean about these kinds of errors. So lie detectors and the law. So this little side story is actually relevant. That's why I wanted to talk about this when we talk about the errors that you can get with these kind of tests. So the question is, well, why is it that we don't just give lie detectors to people all the time, right? Why isn't every criminal given a lie detector test? Well, it's because lie detector tests actually aren't very good. They don't detect lies. It's not a magic box that can sort of know if you're lying or not. What it does is it measures your body responses, your heart rate, stuff like that. People when they lie tend to get slightly nervous, so then their heart rate goes up and stuff like that. The problem is people's heart rate can go up for other reasons too, right? A lot of people, if you're being questioned by the police in the police office and you're hooked up to a bunch of machines, you might be kind of nervous. You might be kind of scared. And the box will read that and interpret it as that you're lying. So it's actually pretty well, you may have watched movies where the lie detector saves the day, but in reality, lie detectors are not great, right? It's kind of the same with fingerprints. In the TV shows, fingerprints always save the day. And in real life, sometimes fingerprints do put people away and make good decisions based on those fingerprints about criminality and stuff like that. But also, if you start to study it, you learn that fingerprinting is not quite as cut and dry as it would seem, right? It's not quite as foolproof as people tend to think it is. Same thing with the lie detectors. So here's what's weird is you'll hear people argue for lie detectors and they'll say, no, these things are 97% accurate. Well, there's 2 problems with that statement. One is if you think about the millions of times those would be used a week around the country, 97% still means a lot of mistakes, right? 3% of a few million is still a lot of people either being let go or not being let go as a mistake for a lie detector. The other thing is it's not symmetric with the mistake. So you might think, oh, well, if it's 97% accurate, then it's 3% inaccurate. So it's like 1.5% each way, right? Where it's either going to say you're guilty when you're not, or it's going to say you're not guilty when you are. But that's not how those errors are not necessarily symmetric. So for instance, with the lie detector, what they're saying is it catches 97% of the people who are guilty, and it catches that 97% of the time. So you go, okay, well, that's still kind of high. But then what you also realize is the error the other way around. What about the people who are innocent and it says are guilty? That happens a lot more. So in this case, the two types of errors would be what? You're guilty and the thing says you're not. But the other one is a lot more likely to happen, which is you're not guilty, but the box says that you are. So in other words, you didn't commit the crime, but the lie detector is saying that you're lying about it. So they think that you did commit the crime. Those errors happen a lot more. So when someone says, oh, well, these machines are 97% accurate, one, that's still not really good enough. But two, you're only counting 1% of the errors. You're not counting all the other side of the errors. So it's disingenuous when they say it's 97% accurate, because you're ignoring that they're up to 50% of the people that it says are guilty actually are not. So it's creating a ton of errors on that other side. Okay, so that's why I think more and more in like these, of course I don't watch them that much anymore, but you'll see more and more like lie detectors are not really used much in these crime shows, because in real life, usually a lie detector is not really considered good evidence anymore. And the same with fingerprints, right? Rarely do they ever get like if you could just get a full perfect fingerprint, then it's pretty good. But that's almost never what happens. What usually happens is you get a part of a fingerprint or a little bit of it. And then when you get into the statistics of how they match a partial fingerprint with, with a person, the science is, it's a little bit sketchy there. There's decisions, like any statistics, there's decisions that have to be made along the way. And those human decisions can ultimately affect whether someone is found guilty or not guilty. So it's not, just when you hear, oh, well, this person there was a fingerprint match. Well, it's not quite that cut and dry. There's errors associated with that the same way as these lie detectors. And usually it's all sorted out with statistics. That's why lie detectors, for the most part, are not used in the court of law anymore. I think they still might be able to use them in like court martials and stuff, but the military trials work differently than like just normal trials. They follow a different sets of protocols and stuff. Okay, so with that, we're out of time. So I believe we still have a little bit more to talk about hypothesis tests. So we'll move forward from there. And then it's not too early to start thinking about your projects and putting those things together. I'm not saying you should finish the whole thing this week, because you probably want to think about confidence intervals and hypothesis tests a little bit. But it's certainly not too late to start organizing your project, thinking about what you're going to do, putting that thing together, thinking about, am I going to use screen capture software? Am I going to use my phone? Am I going to use a camera that I have? How am I going to do this? And, start putting that together. Okay, thanks, everybody. I do have office hours now, so anyone who wants to talk to me, feel free to jump over into Zoom. Otherwise, I will see you next week. Thanks.